Galaxies with the mass of the Milky Way shining less than a billion years after the Big Bang should not exist. And yet, in JWST's deep fields, they're everywhere. To see why this is so shocking, we need to translate what JWST is actually measuring. When astronomers talk about red and blue galaxies, they're not talking about literal crayon colors. They're talking about the spectrum of starlight, how much energy is coming out at shorter, bluer wavelengths versus longer, redder ones. Young, massive stars burn hot and blue, pouring out ultraviolet light. Old, low-mass stars glow cooler and redder. So, in broad strokes, blue galaxies are actively forming stars. Red galaxies are mostly done. That's the basic color age code of the universe. But JWST has found galaxies so massive and so red or blue, so early in cosmic history, that this simple code starts to break down. Let's set the cosmic clock. The universe is about 13.8 billion years old. Light from a galaxy at redshift 10 left when the universe was only about 470 million years old. Redshift 13, roughly 320 million years after the Big Bang. That's not just early. That's barely after the first stars were supposed to ignite. In the standard Lao CDM cosmology, lambda cold dark matter structure grows hierarchically. Tiny dark matter halos form first, then merge into bigger ones, slowly building up galaxies over billions of years. By a few 100 million years, we expect small, messy, low-mass proto-galaxies. JWST, however, is seeing systems whose inferred stellar masses rival or exceed the Milky Way, compressed into this tiny slice of time. These are the so-called monster galaxies. Some of them are extremely red. Their light is dominated by longer wavelengths, even after you correct for the cosmic redshift that stretches light as the universe expands. That redness can mean two things. Either the stars are relatively old, having burned for hundreds of millions of years, or the light is being heavily reddened by dust, tiny solid grains of carbon and silicates that absorb blue light more efficiently than red. Both options are uncomfortable. If the stars are old, they must have formed even earlier, pushing star formation back to times when the universe was only a couple 100 million years old. If dust is responsible, then multiple generations of massive stars must have already lived, exploded as supernovae, and enriched the gas with heavy elements and dust, also requiring rapid, intense star formation. Think of what this implies in terms of growth rate. The Milky Way has built up roughly 60 billion solar masses of stars over 13 billion years. Some JWST red monster candidates pack a similar or larger stellar mass into less than a billion years. That's like building an entire modern megacity, not over centuries, but in a single frantic year. To do this, these galaxies would need star formation rates of hundreds to thousands of solar masses per year, sustained over long periods. Observationally, we infer these rates from their luminosity in the infrared and from spectral features associated with young stars and warm dust. The numbers are extreme. They press against, and sometimes exceed, the theoretical limits set by how fast gas can cool, collapse, and turn into stars without blowing itself apart with radiation and supernova feedback. On the other side of the spectrum are the blue monsters, intensely star-forming galaxies that blaze in the ultraviolet and blue, even after redshift. These are cosmic starburst factories. Their light is dominated by short-lived, massive stars that live only a few million years before exploding. The presence of so many massive stars at such early times tells us that gas is collapsing into stars with astonishing efficiency. In simulations, feedback from those same massive stars, their radiation, stellar winds, and supernovae tends to blow gas out of shallow gravitational wells, throttling star formation. Yet JWST's blue monsters seem to be winning the tug of war, converting a huge fraction of their available gas into stars before feedback can shut them down. Either their dark matter halos are unusually massive and deep, or our models of early feedback are missing something crucial. So how do we actually measure their mass and growth? Astronomers fit the galaxy's spectral energy distributions, essentially the brightness at many wavelengths, with models of stellar populations. These models encode how stars of different masses and ages contribute light by matching the observed colors and luminosities. we can estimate how many stars of what ages are needed. That gives a stellar mass and a star formation history. There are uncertainties. Dust can mimic age, and exotic stellar populations can skew the light. But even with conservative assumptions, many JWST monsters remain uncomfortably heavy and mature. Gravitational lensing, where foreground galaxy clusters magnify background objects, can boost apparent brightness. But careful lens models show that, for many of these galaxies, lensing alone cannot explain away their mass. All of this feeds into what some call a cosmic crisis in cosmology. Let CDM has passed test after test. The cosmic microwave background, large-scale galaxy clustering, gravitational lensing, the abundance of galaxy clusters. It predicts how dark matter halos grow over time and how much baryonic, or normal, matter is available to form stars. If galaxies this massive really exist so early, they may require either more efficient star formation than we thought possible, or an earlier start to structure formation, or both. Some researchers have proposed tweaks. Perhaps the initial mass function, the distribution of stellar masses at birth, was more top-heavy in the early universe, making galaxies brighter per unit mass. Others suggest that black holes and their accretion disks might be contaminating the light, making galaxies appear more massive. A few even flirt with modifying dark matter properties or the expansion history itself. But science thrives on tension between theory and observation. Already, follow-up spectroscopy with JWST is revising some of the most extreme claims downward. Photometric redshifts, estimates based on broad colors, can misclassify nearer, dusty galaxies as very distant ones. More precise measurements of spectral lines sometimes reveal that a supposed redshift 15 monster is actually a more ordinary galaxy, like redshift 5 or 6. Even so, a substantial population of genuinely early massive systems remains. The emerging picture is not that less CDM is broken beyond repair, but that the baryonic physics, the messy details of gas cooling, star formation, feedback, and dust, is far more aggressive and efficient in the early universe than our simulations captured. The monsters are forcing us to upgrade our recipes for how galaxies ignite and grow.